bodies in pure tension and compression, or tension or compression. So we're finally done learning about the stress tensor, how you represent it in new coordinate systems, how a stress tensor in one coordinate system looks when you put it in another coordinate system, going back and forth between stress and strain. And so now finally we're able to start to think about actual loading situations, like how do you come up with the stress and strain for an actual object that's out there in the world with loads applied to it. And the first case that we're going to deal with is objects that are just in pure tension or compression, so just a pure axial load. And yay! Here. Sure. Oh, remind me after, I'll tell you how to use them, but you could probably figure it out, I suppose. Okay, so let's say that you have a force applied this way and this way on an object. And this object has a cross-sectional area A. Then the normal stress produced by those loads is F over A. Okay, so A is the cross-sectional area. And if the value of F is, so if it's in tension, we're going to think of that value of F as positive. And if those arrows are switched to the other direction, that means that it's in compression, and we'll think of that as a negative F. And so then it works out the way that you would expect with the stresses. If the object is being stretched, you have a positive normal stress. If it's being compressed, you have a negative normal stress. And one of the things that's going to be really useful for this is, okay, so look at that picture. It looks like that load is being applied as a point load, right? I mean, that's the way I drew it. But if you really applied, well, first of all, there's no such thing as a point load. Like even the sharpest knife blade makes contact over some amount of area, But if you really applied a point force, then if you thought about how this would deform, as you got up close to where that force was applied, you'd be stretching out. It would be sort of bulging out there, you can imagine. And so the next thing we need to talk about is St. Venant's principle. This is going to be a really useful idea. And if it wasn't for this, our ability to do any useful calculations would be really, really limited. So St. Venant's principle, this is the other kind of principle. What? I think that's, I don't think it's a saint. I think it's a guy's name, unfortunately. That would be cool if it was a saint. So for any load, you can treat the calculation as if it's an equipolant uniform distributed load as long as you ignore points near the load itself. Okay, so up here I drew this body that has these point loads applied to it, and I said, so what I said here is that the normal stress anywhere along this is equal to this, okay, at any point in that body. Okay, well, you know, I said that this force would make that little point bulge out. And so you can imagine if you really knew what the stresses were as you got close to where that point was applied, things would go haywire up near the top and near the bottom. Okay. And as far as we know, things could be going haywire because of that point load all the way through. Okay. If instead of being point loads, those were uniform distributed loads, so this force F was applied uniformly over the whole top and over the whole bottom, then every point really would have that stress. That makes sense, I think. You know, you can think of it up there in terms of the tractions and stuff, and you could calculate that. But so the question is, if we go from the uniform distributed load to this point force, can we treat it like those loads are the same? And St. Venant's principle, which is just an experimental finding, is that, yeah, the stresses in here are going to be basically exactly the same for the point load as they would for the uniform distributed load. The only places where they're going to be different is close to the ends. Okay? So if we don't care too much, if we're going to use other ways to calculate the loads at the ends, we can sort of gloss over the fact that the way the loads are applied might be different in two different cases. Like in other words, if you have a member like this, and you're applying point forces at the ends, as long as you don't trust your calculations right near where the force is applied, the stresses everywhere else in this beam are going to be the same between these two cases, where that distributed load adds up to F or integrates to F. Okay. All right, so if you ignore those end pieces, the stresses everywhere else are going to be the same. Okay. And then, so the question is, how far away do you have to go? So how close to the loaded surface is too close? Well, of course, that's there's no absolute answer for that. It depends on what kind of precision you want and stuff like that. But the generally accepted answer is think of the longest dimension of the loaded face and move that far away from the loaded surface, and then all your stress calculations will be good. Okay, so what that means, so notice that's useful if you have long, slender beams or something. It's not very, in some cases, it just simply means you can't make that substitution. For example, if you had a shape like this, and you apply a tensile force F, well, so the idea is we can do this calculation if we assume that that F is spread uniformly over the face, okay? But then you have to think of the longest dimension of the loaded face, which would be like the diagonal, okay? And you can only trust your results where you're at least that far away from the loaded face, which covers the whole thing, okay? And so in a loaded member like this, there's no part that you should expect to trust according to St. Bernan's principle, okay? So in this case, St. Bernan's principle says the results would be bad everywhere. So what do you do in a case like that where you can't make the simplification and do the calculations the way we're doing them, or you can do it, but the results won't be good? Or what if you want to know what's happening in a beam like this, but you also want to know what's happening at the end? How do you deal with that? Well, we're not going to have the tools to do that in this class. For the most part, you would use, you'd use a more advanced technique. Mainly, people would use finite element analysis, just use a computer simulation at the ends. But what we're going to do gives us a way to do sort of a quick hand calculation that should match up with finite elements. So in a way, you can sort of troubleshoot your finite elements results with the kind of calculations we're doing. And then there are other cases where, sometimes you'll just put so much, if most of the steel in your structure is made up by the bulk of the beam, then you can and you don't want to worry too much about what's happening at the end. Just load up steel at the ends, put big gusset plates or whatever like they do on a bridge. If you ever look at the truss that makes up a bridge, they have thick steel plates that connect the beams together. You don't have to worry about what's happening there. All you have to worry about is, are these gonna, buckle or whatever. Now, using St. Bernan's principle, we can do calculations where members are in pure tension or pure compression. Where's a case where that's going to come up? A really natural place for that to come up is in trusses. And so I want to do just a quick review of truss calculations. So does anyone remember from statics what the definition of a truss is? There's really a pretty short, simple requirement for a structure that you can represent as a truss. Yep, that's getting at it. Yep. So the rule is um, all members are two force bodies. Okay. Um, and the thing about a two force body is, so if you think about an object like this, or even let me make it a complicated shape. It doesn't matter what the shape is. Okay. If there are only two forces acting on this body, and it's still in equilibrium, well, then first of all, we know that those forces have to be equal and opposite, okay? Because otherwise it would be accelerating. And second, okay, so what if there was one force this way and an equal and opposite force that way? That won't work either because that produces a couple and that would make it rotate. So if this is an equilibrium, for a two force body, in equilibrium, the two forces have to be equal and opposite. And act along the line between where the forces are applied. A line, I don't know, maybe between where the forces are applied. Okay, so if one force is here and one force is here, there are only two possibilities. Once you identify the line between those 2 points, it can either be in tension with both of the forces acting away from each other, or it can be in compression and those two forces are pointing towards each other along that line. Okay, so if for a structure, that's made up of two force members, that's a truss. In order to make that happen, you need to have negligible weights for the members. And that has to be the case because if you have a joint on this end and a joint on this end, that's already your two forces. And if you have a third force that's the weight, it wrecks this. Okay, so you have to be able to treat the weights as zero. If you want to include the weights of the members, it's not a truss anymore. Second, all the joints have to be pin joints. So the members have to be connected by pin joints. That's in 2D. In 3D, it would be ball and socket joints. And again, the actual, so that doesn't mean that you can't use the truss simplification if the members have any weight. Obviously, everything has weight. It just means that the forces that are going to be applied to these members need to be big compared to the weights of the members so that it's reasonable to neglect the weights. Mathematically, you have to be able to set them to zero. And it's the same thing with the joints. If you look at the truss, if you look at a bridge and the truss that's used to support a bridge, I mean, it's never ball and socket joints that connect them. Like I said, it's these big bolted gusset plates. So those things are rigidly, really they're fixed joints. You know, they're not ball and socket joints or pin joints. But the calculations that you do using a ball and socket joint or a pin joint give you pretty close results to what you would get with the fixed joint. So you can make that simplification. And then the third one is that all the loads have to be applied at the joints. Because again, if you have a beam with a joint here and a joint here, and then you apply another force in the middle, then again, that's more than two forces. So this simplification won't work. Okay, so it's a lot of simplifications. It definitely, you can't make those simplifications and get good results all the time, but when you can, so if you can make these simplifications or make these assumptions, then you can calculate the loads using the truss simplification. And using this truss simplification cuts down on the number of variables and equations a ton compared to doing a full structure analysis. So for the truss simplification, here's how we're going to do it. So the first thing we're going to do is isolate the whole body as a rigid body, you know, the whole truss. And do the statics of a rigid body. Usually, hopefully, that'll be enough to calculate the external loads on the truss. So there'll be this truss that you could pick up and move, and it would hold its shape. It's a rigid body, but then that rigid body is connected to the ground by, like, say, a pin over here and a roller over here, and you can use that first one to calculate those external loads. And then second, use particle statics at each pin or if you're doing it in 3D, at each pin or ball and socket joint. Assuming that each member is in tension. Okay, well, not every member is going to be in tension. Some are going to be in compression. But the way this works is if you assume that the member is in tension and then you get a negative value for the tension, then it corrects itself. That just means it's in compression, and you can use that value for calculating stresses. So I'm going to do an example. Anybody have any questions before I start? Yep. Yes, the method of joints, yeah. That's what we're going to do. Okay, so let's say this is our truss. That looks a little crooked, but it's supposed to be an equilateral triangle. These are all pin joints, and then this is a roller over here. And we know that all these angles are 60 degrees. And we know that the length of each member is 1 meter. And the only externally applied load is 500 newtons that way. So we want to calculate the tension or compression in each of these members. Okay, before I do that, with this approach, assuming that the weights here are negligible compared to that force, we can use the truss simplification. But if we wanted to calculate what would happen with this 500 Newton force down here a little bit, we can't use the truss simplification. Or if we wanted to, or if one of these was heavier and we wanted to include the weight in one of those members or something. So this truss simplification is a very, it's very picky. And that's something you definitely need to be aware of. Just because you have a structure, you know, that you want to calculate the external loads of the members for, doesn't mean that it's appropriate to use the truss approach. All right, so let's just go through this. It's 2 steps. Let's do them in that order. So the first step is we're going to treat the whole thing as a rigid body and try to calculate the external loads. So free body diagram of the whole thing. We have a pin joint over here. I'll call that force RA. And we have a roller here. I'll call that RB. That's a known direction. And then we have this horizontal force of 500. And we have to choose an about point for the moments. I'm going to choose it here. And now I'm going to write this out in a table. This is the way I do it in statics. So we're going to write out our row vectors, our force vectors, and then take the cross product to calculate the moments. You don't have to do it this way. I know pretty much none of you took statics with me, and no one else does it this way, but this will give you the same answers as your way if you do it right. Okay, so if the row vector is down here, I'm going to first deal with this force RA. The row vector is the vector that goes from the about point to where the force is applied, so that's 0 here. The force vector is just the components, RAX, RAY. Take the cross product, so that's this times this minus this times this, and you get 0 for the Z component of the moment. And then the 500 Newton force, the row vector. So we're looking for the vector that goes from the about point to where that force is applied. Question? Okay, that's going to be positive 0.5, positive 0.866, because that angle is 60 degrees. The force vector is 500, 0. And so the cross product is 433 negative. And then the last one is RB. The row vector is 1, 0. The force vector is 0, RB. So the cross product is positive RB. And now we have this column. That's all our force vectors. Since it's static, we can add those up and set it equal to 0. And then to the moment equation, add those up and set them equal to 0. So Newton's second law says RAX, RAY plus 500, 0 plus 0 RB is equal to zeros. And the moment equation, rotational Newton's second law, says negative 433 plus RB is equal to 0. So from this, we can see that RB is 433. And then we can plug that into the Y equation, and we get that RA has an X component of negative 500 and a Y component of negative 433. Okay, any questions about that? Yeah, so the moment, to calculate a moment, it's this row vector crossed with the force vector. And the meaning of that row vector is a vector that goes from the about point, whatever you choose as your about point, to where the force is applied. It's the same thing that, like, if you tend to just think of it component by component, what you do, let me scroll down. Here is you think, okay, there's an X component of positive 1 from the about point here. You go positive 1, you multiply it by the vertical. It's doing the same thing, but it's just doing it with the whole vector. Yeah, I like this way too. I mean, because your calculator does all these calculations for you, you know. All right, so we have these, and now we can go to the second step, which is one by one to isolate the pins and do those calculations until we have enough equations for the variables. So let me name these. I'll call this one A. I guess I'll call this one B because that's my RB, and then this is C. So okay, let me draw a free body diagram of A. Okay, so there's the pin, a big blown up picture of the pin. And we have a force vector here that I'm going to draw like this. And the components are negative 500, negative 433. And then we have a tension coming from member, well, I guess we have to name these two. Let's call this 1, 2, 3. So if member 1 is pulling on that joint A, then there's a force this way that we'll call F1. And if member 2 is in tension, there's a force this way that I'll call F2. And since we're treating this like a particle, we don't have to deal with moments or anything. We just have to use force equilibrium. So Newton's second law says F2, 0, plus this times the unit vector in that direction, which is 0.5 F1, 0.866 F1. Plus negative 500, negative 433 is equal to zeros. And we have two equations, two variables. This tells us that F1 is equal to 433 divided by 0.866. So that must be 500. And F2 then is positive 250. Yeah. So that tells us that member 1 is in tension with a magnitude of 500. Member 2 is in tension with a magnitude of 250. We still have to get the value for the third one. So now I'm going to do a free body diagram of the pin at B. The forces acting on B are the reaction RB, that's 433 acting up. There's the force applied by member 2, that's a tension value of 250. And then there's this unknown force F3, but we know the direction. And so Newton's second law here says 0, 433 plus negative 250, 0 plus negative 0.5 F3 positive 0.866 F3 is equal to zeros. And so F3 is equal to negative 500. And we don't even need the y equation. Okay, so, well, any questions about that calculation? Yeah. Yeah. If you assume that it's in tension, then the sign tells you tension or compression. So, um, and then you can just use this value directly. You can use in the stress calculation. So now let's say if each beam had a cross-sectional area of 1.0 times 10 to the minus third area, meters squared. Okay. What are the stresses in each of these? Well, for each one, let's assume that the x-axis, so we can use different coordinate systems for each one of these, that's fine. So let's assume that the x-axis is along the loading axis of the beam. Then member one, the x stress for member one is positive 500 divided by 1 times 10 to the minus third. And so that's 5 times 10 to the fifth pascals. For member two, we have positive 250 divided by the cross-sectional area. And so we get 2.5 times 10 to the fifth pascals. And then for member three, we have negative 500 divided by 1.0 times 10 to the minus third. And so you get a stress, an XX stress of negative 5.0 times 10 to the fifth. Okay. So what you get is one of these with a value of 5 times 10 to the fifth. One of them with a value of 2.5 times 10 to the fifth. And the last one with a compressive stress of 5 times 10 to the fifth. All right. One thing that's sort of interesting, so, and now those represent stress tensors, so you could go to the stress tensor and then you could calculate principal stresses and whatever. Well, what's the principal stress for, let's say this one, what's the principal stress tensor? Do it in your head. Yeah, right, it's already principal because the only stress is normal. And so what's the maximum shear stress? Yep, 2.5 times 10 to the fifth. Okay. And now, this is a harder one. Where is this? So let's think about it. Let's think about it this way, okay? So the maximum shear stress is 2.5 times 10 to the fifth, okay? What angle is that shear stress face acting on? Well, remember that, yeah, forget that. But the answer is that face would be tipped 45 degrees because that's what you have to do in order to find the stress tensor with the maximum shear. And that actually has a practical application in materials that are really brittle. If you have a pure compression fracture of, say, a bone, but it happens in other brittle materials too, what you see always is that the bone, so like in car accidents, people's feet hit the front of the, by the pedals, they get compression fractures in their legs. What that looks like is a fracture at 45 degrees, like this, because brittle materials are very bad at handling shear stresses. And so it fails in shear. And if it's going to fail because of shear stresses, it's going to happen at on that first face where the shear stress is big enough, and that's at that 45 degrees.